Hey guys, today we're going to learn about the fundamental theorem of calculus, also called the FTC. Now what the fundamental theorem of calculus is that it allows us to find the actual value of a definite integral. In the previous lesson on Riemann sums, we learned that we can use rectangles and trapezoids to estimate the area below the curve, and that's bounded by the x-axis. However, this theorem, if f of x is continuous on the interval a to b and differentiable, then that means that the integral from the interval a to b of f of x dx is equal to the antiderivative of f of b minus the antiderivative of f of a. So here we have this particular function where f of x is equal to negative 2x plus 3. We're going to calculate the definite integral using the fundamental theorem of calculus, and then we're going to verify that answer by calculating the area that is bounded by the graph and the x-axis. So first, in order to find the antiderivative of negative 2x plus 3, we would have to add 1 to the exponent and then divide by that new exponent, leaving us with negative x squared, because the 2's would cancel, and then plus 3x. Now, normally we would write plus c, but when we are integrating with a definite integral, we never write the plus c. And that's because since we're going to be subtracting anyway, if we're going to add c here and then subtract c here, the c's would end up canceling regardless. So just so you understand notation, once you find the antiderivative, what you do then is you can put this in parentheses to indicate that we're going to evaluate this using the fundamental theorem of calculus. And then you're going to put a bar. And then on this bar, you put the interval with which you are evaluating. So we're doing from negative 2 to 1. So this indicates that we are evaluating using the FTC this entire function, that's why it's in parentheses, followed by the bar indicating the interval. So now we plug in b, which is the top number. So we plug in the 1, and we would get negative 1 squared plus 3 times 1. And now we're going to subtract when we plug in a, which is negative 2. So negative 2 squared plus 3 times 2. And now we just work this out. 1 squared is 1, so this gives me negative 1 plus 3 minus, and anytime you have the minus using the FTC, put whatever it is that you are subtracting in parentheses to make sure that if you need to, you would have to distribute the negative or work out what's inside of the parentheses first and then subtract. So this gives us 2 squared, which is 4, and then we have the negative. So negative 4 plus 6. Now negative 1 plus 3 is 2. Oh, this is a negative 2, sorry. It's negative 2. Regardless, this would still give us negative 4, and then this would be minus 6. So minus negative 4 minus 6, which is negative 10. So 2 minus negative 10 is 2 plus 10, so we get an answer of 12. Now we're going to verify that using our geometry. So we do need to know some geometry equations in order to calculate that area. We are focusing on the interval negative 2 to 1. So what we do is we use the x-axis to bound the area, and then for the shape, we go up to the function. And so this is the integral with which it's defined. What we have here is a trapezoid. And the area of a trapezoid is A is equal to 1/2 times the height times base 1 plus base 2. Now this trapezoid is on its side because remember a trapezoid, you have the parallel sides. So it's this side here that's parallel to this one. And then the height is perpendicular to those sides. So the height is the x-axis. So we have 1/2 times the height, which is 3 units, times base 1, which is 7 units, plus base 2, which is 1 unit. This will give me 1/2 times 3 times 8 3 times 8 is 24, and half of 24 is equal to 12. And you see how we end up with the same answer. Let's try that with a couple of other examples. We're using the same exact graph for each one. So for the antiderivative, it's still going to be the same, which is the negative x squared plus 3x. But this time we are evaluating from 2 to 5. So we're going to plug in the 5. So negative 5 squared is negative 25 plus 3 times 5, which is 15. Minus, now I'm going to plug in the 2. Negative 2 squared is negative 4 plus 3 times 2, which is 6. Negative 25 plus 15 is negative 10. Minus negative 4 plus 6 is 2. And negative 10 minus 2 is negative 12. Now you're probably wondering how we get a negative area. Now when we look at the geometry equation, you'll see why. So we're evaluating from 2 to 5. Remember that the area is determined by the x-axis and the graph. So we can see here that this trapezoid, which is the same trapezoid that we had earlier, it's just now it's on the other side and below the x-axis. So if the area that you're calculating is below the x-axis, that means that we would have a negative area. And again, just so that you can see how it's the same thing, this is 1/2 times the height of the trapezoid, which is 3, times the bases, which is 1 plus 7. And because this is below the x-axis, we would make that area negative. So this gives us that negative 1/2 times 3 times 8, which is 24. So we have negative 12 for the area. Now when we look at this one, we're evaluating the same exact graph, but from negative 1 to 4. So we have the negative x squared plus 3x, but now we're evaluating negative 1 to 4. So we're going to plug in the 4. Negative 4 squared is negative 16, plus 3 times 4, which is 12, minus. Now I plug in the negative 1. Negative 1 squared is positive 1, and then we have that negative, so minus 1, plus 3 times negative 1, which is negative 3. Negative 16 plus 12 is negative 4, minus negative 4, which gives us negative 4 plus 4, so we get an area of 0. And this is why that happened. If we're evaluating from negative 1 to 4, what we get here is we have a positive area for this triangle, and then we have a negative area for this triangle. If we were to calculate each individual area, the area of a triangle is 1/2 times the base, which is 3, times the height, which is 5. For this triangle, because it's negative, that means because below the x-axis it's negative, so negative 1/2 times the base, which is 3, times the height, which is also 5. So see how we get this area and this area, this is positive and this is negative. And since they're the same triangle, that means that they would just cancel out and give you an area of 0. Now, to kind of sum this all up, this is what we should take from what we just did. We already saw that the integral from a to b represents the area of the region bounded by the function and the x-axis. If the area is greater than 0, that means that the region bounded by the function and the x-axis is larger above the x-axis than below the x-axis, meaning that it is a predominantly positive area. So the graph is above the x-axis more than it is below the x-axis. And then vice versa for if the area is negative, then that means that the area is predominantly below the x-axis. If the area is equal to 0, then that means that the area above the x-axis and the area below the x-axis are equal. Now here we have this graph of f of x. We have areas that are on top of the x-axis, and then we have areas that are below the x-axis, and that's why it's indicated with the plus signs for positive and the minus signs for negative. So if we were to evaluate from -3 to 1 of f of x dx, if I look here from -3 to 1, most of my area is below the x-axis. So this integral here would be predominantly negative, or rather the area that we would get would be a negative area. Then if we were evaluating from 0 to 4, the area is predominantly above the x-axis, so that means that this area would end up being positive. So now let's apply these geometry principles to some of these integrals. Here we have this graph that consists of some line segments as well as a semicircle. As a reminder, I put here all of the areas that you should know by heart. The area of a trapezoid is 1/2 times the height times base 1 plus base 2. The area of a rectangle is base times height. The area of a triangle is 1/2 of base times height. And the area of a circle is pi r squared. If I wanted to find the area for this integral from -4 to 4, that is from here to here. And we see here that we have this triangle, this semicircle, and this other triangle. When we're calculating for this integral, since this triangle is below the x-axis, that means that it is a negative area. So we would put -1/2 times the base, which is 2, times the height, which is 1. Then the semicircle is also below the x-axis, so I would subtract that area as well. Now the area of a circle is pi r squared. So since this is half of a circle, we would use 1/2 times pi times the radius, which is 2 squared. Then finally, for this triangle here, that is above the x-axis, so I would add that area, which is 1/2 times the base, which is 2, times the height, which is also 2. And now to get the value of this integral, we're just going to work this out. So this 1/2 and this 2 will cancel, leaving me with -1. This here is 4. So 1/2 of 4 is going to be -2 pi. And then here this 1/2 and this 2 will cancel, so plus 2. So now we just combine. -1 plus 2 is +1, and then the -2 pi. So this would be the value of that integral. Next, we're going to do the integral from 0 to 5 of f of x dx. So we're looking at from here to here. So we have here this quarter circle now. And then what we can do here is we can split this into the triangle that we already found. And then this is a trapezoid. So that quarter circle, so that's 1/4 of a circle. So I would use 1/4 pi and then the radius squared. And it's because it's below the x-axis, I'll make this area negative. Then I'm going to add the area of that top triangle, which we found to be this one here. So that is +2. That's the area of that triangle. Plus the area of the trapezoid, since it's also above the x-axis. So that would be 1/2 times the height, which is 1, times base 1, which is 2, plus base 2, which is 1. So this is 2 squared is 4, and divided by 4 would give us -pi plus 2 plus, then this is 3 times 1/2, so 3/2. In order to at least combine these here, I need to put the 2 over 2. And if I put it over 2, I have to multiply the numerator by 2. So this would give me -pi plus 4/2 plus 3/2, which gives me a final answer of -pi plus 7 over 2. Now we're going to look at how to calculate these areas, and we're going to verify our answer with the calculator. So we have here the integral from -1 to 2 of 2x minus x squared. So first we're going to apply that fundamental theorem. So I have to add 1 to the exponent and then divide by that exponent. So 2x squared divided by 2 minus x to the third divided by 3. And we're evaluating this from -1 to 2. I can at least simplify these 2's here. So this gives me x squared minus x cubed over 3. And then we're evaluating it from -1 to 2. So now let's apply that fundamental theorem. So we're going to plug in the 2. So 2 squared is 4 minus 2 to the third, which is 8 over 3. Minus, now I plug in the -1. -1 squared is 1. Minus -1 to the third is -1. And then we have it, this is the minus. You know what, I'll just do it all in pieces. So it'll be -1 over 3. So because it says negative and negative, we make it positive. Now what I like to do here is, instead of finding a common denominator and such here, since these two have a common denominator, I'm going to distribute this negative and then just combine those two fractions and see what happens. So this gives me 4 minus 8 over 3 minus 1 over 3. 4 minus 1 is 3. And negative 8 over 3 minus 1 over 3 is negative 9 over 3. Which negative 9 over 3 is 3. So 3 minus 3 gives me an area of 0. So now we're going to verify that with the calculator. I'm going to go ahead and graph that function that we have here, which is the 2x minus x squared. So when you want to use the calculator to integrate, you put the actual function that you are integrating, because the calculator would do that work for you. So now I'm going to graph it. And we have this. Now I'm going to shorten my window a little bit just so we can see the graph a little better. So I'm going to, since we're evaluating from -1 to 2, I'm going to put -2 to 3, because I like to leave a little bit of wiggle room in there. And I'm going to shorten my y values to -4 to 4, just so that it's closer in my graph here. So this is the area that we're concerned about there, from -1 to 2. So now what we do is we go to the second calc menu, and in option 7 we have the option to integrate. So we're going to click on 7. It's going to ask you for the lower limit. So the lower limit is the number on the bottom, so the smallest number. So I'm going to put -1. And then it's going to ask you for the upper limit, which is the value of b, so 2. And what it does is it shades the area already for you, and then it'll give you the value of that integral. Now here it says -1.5 e to the -14. This is kind of like scientific notation. Whenever you see the e, that means that it's 10 raised to the exponent of -14, meaning that we move this decimal over to the left 14 times. So that's what a negative exponent here means after the e. Move the decimal to the left that many times. If it was a positive exponent, like if it was e positive 14, then you would move the decimal to the right 14 times. Now, since we're moving this decimal to the left 14 times, then that's -0.00000, etc. 15, which essentially is 0. So that's why we got this answer of 0. Now, we're going to do the same thing, but with the other graph, which we'll get to in a moment. Let's first work this out by hand. So here we're evaluating the integral from -2 to 3 of 1 over x squared minus x. So I'm going to want to rewrite this so that it's easier to integrate. This is the same thing as saying from -2 to 3 of x to the -2 minus x dx. Now I can find the antiderivative of this by adding 1 to the exponent. So if I add 1, that's x to the -1 over -1, which would just make this negative, minus x squared over 2. Again, I want to rewrite this so it's easier to find that value. So this is -1 over x minus x squared over 2. And now we're ready to plug in our limits here of integration. This is a 2. So first we plug in the 3, and we get -1 over 3 minus 9 over 2. Now I'm going to plug in the -2. So -1 over -2 is a positive 1 over 2, minus -2 squared is 4 over 2. Okay, so now we work this out. We have this -1 over 3 minus 9 over 2 minus, and then this is -3 over 2, making this plus 3 over 2. We can combine at least these two fractions, so we get -1 over 3 minus 6 over 2, which if I want to, which 6 over 2 is just 3. So -1 over 3 minus 3, I need to put this over 3 and then multiply the numerator by 3. So we end up with -1 over 3 minus 9 over 3, which is equal to -10 over 3. Now we're going to see what happens when we put this into the calculator. When I put it in the calculator, you could put it as a fraction, so you would open a parentheses and do 1 over x squared, or you can put the one that you've rewritten with the negative exponent. That's the one I'm going to choose to put. Either one is correct. I just don't like having to type in fractions, just because if you don't put parentheses, it'll do it wrong. So we're going to do x raised to the -2 plus, oops, not plus, minus x. And now we're going to graph it. So now we're evaluating this integral from -2 to 3. So I'm going to go to my second calc menu. -2 for my lower limit, 3 for my upper limit. And you're going to see now that it's going to think for a very, very long time. And eventually it's just going to stop. And the reason why it's not calculating the integral is because we have violated that condition of the fundamental theorem of calculus. In order to be able to integrate, the function has to be continuous. And this function on that interval, -2 to 3, which is exactly what you see here, we have a vertical asymptote at x is equal to 0, meaning that that area will not be enclosed, so it will not be able to find that integral. So this value is irrelevant. And in fact, this integral does not exist. Let's see if it's still thinking. Yeah, basically. We can just clear this out. See, it says here, error, break. That's fine. Quit. Okay. Let's try a couple more, just to make sure we understand how to use the calculator. We have here the integral from 1 to 4 of 2x plus 3 over x squared. So first we're going to do all of these by hand. We need to rewrite this so that it's easier to integrate. So since 2x plus 3 is getting divided by x squared, you can divide the 2x by x squared and divide the 3 by x squared. So that way we can split it up. So this is the same thing as saying from 1 to 4 of 2x divided by x squared, which is 2x to the -1, plus 3x to the -2. Remember that what you do in order to simplify, you subtract the exponents. So since this is an exponent of 1, 1 minus 2 is negative 1. Here there is none, so you just bring up the x squared, making it x to the negative 2. Now here, the 2x to the negative 1, when we try to find that antiderivative, remember that if you add 1 to the exponent, that would be 2x to the 0. And then you have to divide by that new exponent. Since we have over 0, that cannot be done. So that does not work. That must mean that this is an ln function. So this, let me rewrite this one more time so that it's easier for you to see. This is the same as 2 over x plus 3x to the negative 2. And 2 over x, that's basically 2 ln of x. Because if I were to rewrite this as 1 over x, because the 2 is just a coefficient, that 1 over x dx is the ln function. So that's why this is 2 ln of x. And now I'm going to add 1 to this exponent, so 3x to the negative 1, and then divide by the new exponent, which is negative 1, making this negative. I can rewrite this so that it's easier for me to plug in these values as 2 ln x minus 3 over x. And now we're going to plug in the 4 and then subtract when we plug in 1. So when you plug in the 4, you get 2 ln of 4 minus 3 over 4 minus, now I plug in the 1, 2 ln of 1 minus 3 over 1, which is just 3. Now the ln of 1 is just 0. So this is basically 0. So we have now 2 ln of 4 minus 3 over 4 plus 3. Since 0 minus 3 is negative 3, and minus negative 3 will become plus 3. Now I want to actually be able, just so that I can verify this with the calculator, I want to get the decimal for right now, just for the purpose of this exercise. So that way we can verify our calculator answer. So I'm just going to put all of this into the calculator and see what I get. So we have 2 ln 4 minus, anytime you put a fraction, put it in parentheses. So it only divides the 3 over 4. And let me actually close this parentheses here. Minus 3 over 4 plus 3. And we get a value of 5.0225. So now let's go to the calculator and graph it and integrate. We have here 2x plus 3, and notice that I put the whole numerator in parentheses, divided by x squared. Now I have my previous window that does not include 4, so I'm going to adjust my window. I'm just going to leave it now to the standard viewing window. And let's graph. So this is my function, and you can see that there's a vertical asymptote here at 0, but that doesn't matter in this case because we are integrating from 1 to 4. So 0 is outside of that interval. So now we're going to go to the second calc menu, option 7 to integrate. Our lower limit is 1, and our upper limit is 4. And we get the same value that we got by hand, the 5.0225. All right, let's move on to this next one here. We're going to integrate 2x plus cosine x. The antiderivative of 2x is x squared, because if you add 1 to the exponent and then divide by 2, those 2's will cancel. And then the antiderivative of cosine x is sine x. And we're evaluating this from 0 to pi. So now we plug in the pi and we get pi squared plus sine of pi minus 0 squared, which is 0, plus sine of 0. Now we have pi squared, the sine of pi is 0, minus, and then we have 0 plus the sine of 0, which is also 0. So this is all basically 0. So our answer here is pi squared. So I'm going to do the same thing and get that actual value so we can verify with the calculator. So second pi squared is 9.869. I missed that last number, which is 6. Okay, so now we're going to graph and see if we get the same answer. So remember, we input the original function, so 2x plus cosine x. Let's graph it. And now we're going to integrate from 0 to pi. And see, we get the same value, 9.8696. So everything has been verified with the calculator. So now we're going to set the calculator aside and look at how to use the fundamental theorem of calculus using charts. So they love using these kinds of charts in AP exams where you're given the x values and then several types of functions. You have the function, you have the derivative, and you have the second derivative. So for this first, for part A, it says to integrate f prime of x from -3 to 1. Now when you're integrating f prime, what you get is f of x. And then we're applying the FTC from -3 to 1. So this is going to equal to f of 1 minus f of -3. And now we just look at the chart for those values. F of 1 is -2 minus f of -3, which is 4. And we end up with a value of -6. Whenever you're evaluating using the FTC, and especially with function notation, make sure that you write the function with those numbers inputted before you substitute with the actual values from your chart. This shows the reader that you know what you're doing, and it also allows you to check your work in case maybe you plug in wrong numbers. You know exactly what you need to look for in your chart. Now here we have the integral from 1 to 5 of 3f double prime of x. Now 3 is just a constant, so we can take that constant and move it to the outside. So this is the same thing as saying 3, the integral from 1 to 5 of f double prime of x dx. Now you can do that or you can leave it, it's completely up to you. But regardless, it's not a constant, coefficients, just kind of tag along whenever you're finding derivatives or antiderivatives. So the antiderivative of f double prime is f prime. So I can leave the 3 on the outside and integrate f prime of x from 1 to 5 and apply the FTC based on that. And then multiply the 3 afterwards. Or you could put the 3 inside and multiply as you go. That doesn't matter. So we're going to plug in the 5. So this is 3 f prime of 5 minus f prime of 1. Now we use our chart. So 3 f prime of 5 is 2 minus f prime of 1, which is 0. So this gives me 3 times 2, which is 6. Now over here we have the integral from -1 to 3 of f prime plus f double prime. So when you integrate, this is going to be f of x plus f prime of x. And we're evaluating this from -1 to 3. So now we plug in the 3 and we get f of 3 plus f prime of 3 minus, and now we plug in the -1, f of -1 plus f prime of -1. Now we're going to use our charts to substitute those values. F of 3 is 1 plus f prime of 3, which is 3. minus f of negative 1 is 0, plus f prime of negative 1, which is 1, leaving me with 4 minus 1, which is 3. Moving along to this next one here, we have the integral from negative 3 to 3 of half of f prime plus 2 f double prime. So when we integrate, that's going to be 1/2 f of x plus 2 f prime of x. And we're going to evaluate this from negative 3 to 3. So we got to plug in those function values. So 1/2 f of 3 plus 2 f prime of 3 minus, now we're going to plug in the negative 3. 1/2 f of negative 3 plus 2 f prime of negative 3. Now let's substitute these function values with what's in the chart. So we have the 1/2 f of 3, which is 1, so just 1/2, plus 2 times f prime of 3, which is 3, minus 1/2 f of negative 3, which is 4, plus 2 f prime of negative 3, which is negative 2. Okay, so far we have this 1/2 plus 6 minus, then in here, this half of 4 is 2 plus negative 4, so minus 4. So this is what we got now. We have the 1/2. Now this is 6 minus negative 2. So 6 minus negative 2 is 6 plus 2, so plus 8. We're going to need to be able to combine this. We need to put 8 over 2 and therefore multiply 8 also by 2. So this is 1/2 plus 16 over 2, which is equal to 17 over 2. Now for this last question here, it's not an integral question, but this is where some of us struggle, which is using those tangent line approximations. So we're going to review that really quickly. In order, let me just read this. It says, use a tangent line approximation to estimate the value of f of 3.1. Is this an over or under approximation, and justify? So if we're going to do a tangent line approximation, that means that I need to write the equation of the tangent line for when x is equal to 3. And I use 3 because if we're approximating for 3.1, then I need the closest value to that number that would be on my chart, which is 3. So in order to write the tangent line for when x is equal to 3, I need my point of tangency. F of 3 is equal to 1. And then I also need my slope of tangency. So f prime of 3, the derivative, is 3. So now I'm going to write that equation of the tangent line, which would be y minus 1 is equal to 3 times x minus 1. Now I'm ready to approximate, so I'm going to plug in 3.1 for x. So y minus 1 is equal to 3 times 3.1. Oh, sorry, this was 3, because that was the x value. 3.1 minus 3. Now what I get here is y minus 1 is equal to 3 times 3.1 minus 3, which is 0.1. 3 times 0.1 is 0.3. So to solve for y, I would just have to add the 1, giving me an approximation that f of 3.1 is approximately 1.3. Now to determine if this is an over or an under approximation, that depends on the concavity at that x value. So f double prime of 3, if I look here, is negative. So it's less than 0, meaning that my graph is concave down. So if my graph is concave down, that means that the tangent line would be above the curve. So this is an over approximation. And the reasoning is because f prime of 3 is less than 0. So now let's jump over to properties of integrals. Now, some of these properties we've kind of already been using. So first off, if you have a function that you are integrating that is f of x, and then you're adding or subtracting another function, or just parts of a polynomial, you can essentially separate it into two separate integrals integrating from the same intervals. So as you can see here, this is one integral of f of x plus or minus g of x, and then it can be separated to the integral of f of x plus or minus the integral of g of x. Now, if you have the integral from b to a rather than a to b, what that means is that the lower limit is actually on the top and the upper limit is on the bottom. And what you can do to fix that is just reverse those limits, right? So that the lower limit is on the bottom as it should be, and the upper limit is on the top. But then that means that that integral would be negative. If you have an integral that is from a to b, and then you're adding an integral of the same function but from b to c, then that's the same thing as if you were just integrating from a to c. So if it connects at b, you can just add them all together, and that gives you one integral. Now this is one that we've used before. If you have a coefficient here, like k, then what we can do is we can move the k to the outside, like here, and that would be your integral. And then finally, if you have an integral from a to a, meaning the upper limit and the lower limit are the same number, then that's just going to equal to 0 because it would not consist of any area, but instead just be a point. Now, these two apply for even and odd functions. This first property is for an even function, meaning that it is symmetric along the y-axis. If it is symmetric along the y-axis and you are integrating from negative a to a, the area on the left side of the y-axis is the same as the area on the right side. So you can either write this as double the area from 0 to a, or double the area from negative a to 0. So like if you're told that f of x is an even function and you only know the value from 0 to some number, then you can just double it in order to get the entire area. Now for an odd function means that it is symmetric along the origin. So if you're integrating from negative a to a, then that means that the area above the x-axis is going to equal to the area below the x-axis, and therefore that area would equal to 0. Now let's apply some of these properties. We are told here that if the integral from 0 to 3 of f of x dx is equal to 6, and the integral from 3 to 7 of f of x dx is equal to negative 8, we're going to find the value of all of these integrals. So first we see here the integral from 0 to 7. Now if you notice, we have from 0 to 3, and then we have from 3 to 7. So we can essentially rewrite this integral to be the integral from 0 to 3 of f of x dx plus the integral from 3 to 7 of f of x dx, since I know those values. The integral from 0 to 3 is 6, plus the integral from 3 to 7 is negative 8. 6 plus negative 8 is 6 minus 8, which is negative 2. Now here we have the integral from 7 to 3 of 3 f of x. First of all, we can take this 3 and move it to the outside. So this is the same thing as saying 3, the integral from 7 to 3 of f of x dx. Additionally, you should notice those limits of integration here are reversed, because the lower limit should be on the bottom and the upper limit on the top. So we want to reverse that back, and this would make the integral negative. So this would be negative 3, the integral from 3 to 7 of f of x dx. Now I know this value that was given to be negative 8, so this is going to equal to negative 3 times negative 8, which is 24. Over here, we have the integral from 0 to 7 of 2 minus 4 f of x dx. For this one, I don't know what this value would be if I were to integrate it right away because it's not given. So we can actually separate this. This is the same thing as saying the integral from 0 to 7 of 2 dx minus the integral from 0 to 7 of 4 f of x dx. Additionally, I can take this 4 and move it to the outside. So again, this is 0 to 7 of 2 dx minus 4, the integral from 0 to 7 of f of x dx. Now this I'm going to have to actually integrate and use the FTC. So the antiderivative of 2 is 2x, and I'm going to evaluate that from 0 to 7 minus 4, and then the integral from 0 to 7 I found here in part A, which is negative 2. When I plug in the 7 here for so we can get this value, we get 14 minus, when we plug in 0, which is 0. And then minus 4 times negative 2, which is plus 8. So what we're doing here is 14 plus 8, which is 22. For this last one, it says to evaluate the integral from negative 3 to 3 of f of x dx if f of x is an even function. Now, if it's an even function, that means that this integral is double the integral from negative 3 to 0 or from 0 to 3. We have the one that's from 0 to 3. So we can rewrite this as 2, the integral from 0 to 3 of f of x dx, which we know that that number is 6, so 2 times 6 gives us 12. Now we're going to use these properties along with graphs. Here we have the graph of f of x, and we want to evaluate all of these integrals. So we have first here the integral from 0 to 3. So here we got to use a lot of geometry. Here we have 0 to 3, 0, and then here's the 3. So we can split this up. This looks to me like a quarter circle and a trapezoid. So when I'm trying to find this area, it would be 1/4 of pi, and then the radius of this circle is 2 squared, plus the area of the trapezoid, which is 1/2 times the height. The height here is 1, since remember it's perpendicular to the parallel sides. So the height is 1 times base 1, which is 2, plus base 2, which is 3. So this gives me 2 squared, which is 4, which cancels out with the 1/4, so pi, plus 1/2 times 5, so 5/2. So this would be that integral. For this next one, we are evaluating the integral from 0 to 4 of f of x dx. Now, if you're using the properties of integrals, the integral from 0 to 4 is the same thing as saying the integral from 0 to 3, which we already got, dx, plus the integral from 3 to 4 of f of x dx. Now, in this particular case, if you look at 3 to 4, it's a negative area. So we could also just subtract it. Now, we can also just write this as, because this is a negative area and this will cancel out with this area here, we can also say that this integral is equal to the integral from 0 to 2 of f of x dx. Whatever way you prefer to look at it is fine. So you can take your previous answer and then just subtract the area from 3 to 4, or you can just recalculate the area from 0 to 2. It's completely up to you. Now, if I just do from 0 to 2, then that's the area of this quarter circle, which we found to be pi, plus the area of this rectangle, which is 2, the base, times 1, the height, so 2. So that would be the value of that integral, however you prefer to look at it. You can also have done this one, which I'll do down here, which is the pi plus 5 over 2 minus the area of this triangle, which is the 1/2 times the base, which is 1, times the height, which is also 1, which gives you pi plus 4 over 2, which is equivalent to pi plus 2. So regardless of which way you do it, you would get the exact same answer. Now for this last one, we are evaluating the integral from -3 to 3. Now if we look at this graph, I'm going to erase these markings here, this is an even function because it is split up right down the y-axis and it's symmetric on the left, on the right. So we already got the integral from 0 to 3. So we can restate this as 2 of the integral from 0 to 3 of f of x dx, which I already found. So this is 2 times pi plus 5 over 2. If you distribute the 2, you get 2 pi plus 5, and that would be the value of that integral. You can also most certainly find the actual value from -3 to 3 by calculating all of that area, but that would be a little bit more work. Not that it's wrong, but this would be a nice little shortcut. Now we're going to do one more thing here. We're going to find the function value from a definite integral. So here we are told, if f of -3 is equal to 5, what is the value of f of 4? Where f of x is the antiderivative of f of x. So notice the capital F, that is the antiderivative, so the integral, and little f of x, that is the original function, which is what we have here. So we are told that f of -3 is equal to 5. So right here, even though, obviously remember that this is for the antiderivative, not the function. And we are trying to find f of 4. So what we can do here is we can apply the fundamental theorem, because we know that if I were to evaluate from -3 to 4 of f of x dx, that gives me capital F of 4, or rather, let me restate that. Let me not skip ahead. The antiderivative of f of x is capital F of x, and we would evaluate that from -3 to 4, which is equal to capital F of 4 minus capital F of -3. Now the reason I do this is because I know the value of capital F of -3, and I'm trying to find capital F of 4. And I could actually find out what the whole value of this integral is by applying my geometric equations. So here what we have, in order to get the value of this integral in its entirety, we have a trapezoid here. We have this semicircle, but it's above the x-axis, so we need this area here, which we can actually calculate by finding the area of the rectangle that is formed and subtracting the area of that semicircle to get the leftover shaded part, which is what I need. Then these areas here, these would cancel. So we can essentially just ignore this part of the graph. So let's see if we can calculate the area. We have the trapezoid, which is 1/2 times the height, which is this one here, so 3, times base 1, which is 3, plus base 2, which is 1. Then I'm going to add the area of this rectangle, which is 2 times 1, so 2, but I'm going to subtract the semicircle so that it leaves me with that shaded region, which is 1/2 times pi times the radius squared, which is 1, and 1 squared is just 1. And that's going to equal to capital F of 4 minus capital F of -3, which is 5. So see, like this, I've created an equation that allows me to solve for f of 4. So this is 1/2 times 3 times 4. 3 times 4 is 12, and half of 12 is 6. plus 2 minus 1/2 pi is equal to f of 4 minus 5. 6 plus 2 is 8. Minus half of pi is equal to f of 4 minus 5. So in order to solve for f of 4, we would just add 5 to both sides. And that would give me that f of 4 is equal to 13 plus, minus, my bad, minus half of pi, which I'm just going to write as pi over 2. So that's how we would find a function value. So what we do is we take the value that's given, that's going to be one of my limits of my integral, and then the value that I'm looking for will be the other limit of my integral. And then you set your derivative, you find the geometric value, the value of that integral using geometry, and then you use the fundamental theorem of calculus at the same time. So now here, this is a calculator question, and we'll get to that in a moment. It says, let f be a differentiable function such that f of 3 is equal to 2.345 and f prime is equal to the ln of x squared plus 1. What is the value of f of 5? So I'm given f of 3 and I want f of 5. So these numbers here are the limits of my integration. So I'm going to set my integral here from 3 to 5 of f prime of x. I'll rewrite this in a second just so you understand where I'm getting at. And this is going to equal to f of 5. I keep skipping a step and I apologize. To f of x evaluated for 3 to 5. So this f prime of x, that is the ln of x squared plus 1. So my integral of 3 to 5 of ln of x squared plus 1 dx is going to equal to f of 5 minus f of 3. So this, remember the calculator does this. I can go to my calculator here. I'm going to go to my y equals, I'm going to clear this out and put in this function. So ln of x squared plus 1, enter. Let's graph. Now we are going to integrate. So second calc, my option 7 from 3 to 5, which gives me 5.61, let me see, 5.6314, 6314, and that's going to equal to f of 5 minus f of 3, which was given, the 2.345. So to solve, I just have to add 2.345 to both sides. So we get that f of 5 is going to equal, let's put that into my calculator here. So 5.6314 plus 2.345, and we get a value of 7.9764. And that would be the value. All right, and that's the fundamental theorem of calculus.